I'm Adam Nicholls, the head of engineering here at Credit Kudos. I'll quickly talk to you about who we are and then sort of two topics here around the technicals and challenges that we've had recently and where we're going. So Credit Kudos is a challenger credit reference agency. We were one of the first in the UK to combine open banking and loan outcome data. We enrich complex raw transactional data to enable better and faster decisions. And we've built insights on hundreds of millions of data points over the last 5 years. So some of our partners up here, there's lots of them. This is an exhaustive list, but some household names that we can see there: Admiral, Drover, Car Finance 24/7, among many others. So what do we actually do? So there's a few areas that we kind of cover. We first of all cover income verification. So using open banking, we can work out how much income you have per month, when you get paid, how often you get paid, and whether it's stable. We can also look at affordability insights, so we can work out whether you've got money left over at the end of the month and what your expenditures are and what you're spending your money on. And then we also drive out insights as well, things like risk, so flags for missed payments, dipping into your overdraft, gambling, and other things that lenders might be interested in when they're looking to process a loan application. We also look at fraud prevention as well. So using open banking, we get access to a lot of account information that we can use to match against loan applicants and things like that. And we also look at customer management as well. So how it works, so at a high level, we've got this sort of flow where we have a product called Connect, which will allow somebody looking for a loan to connect to their bank account through open banking. We can fetch that information. And then we take that raw transactional data and we categorize it and optimize for accuracy and coverage. And then finally, once we know where you're spending your money each month, we can look to create scores and enrichment and insights around it, which helps lenders at a high level understand what they should be looking for when they're kind of processing applications or assessing. So the Connect product itself is our open banking journey. It can be embedded into any website, mobile application. We also send out email invites and SMS text messages to invite people to come and link their bank account. The journey asks someone, basically using the open banking system, to OAuth into their bank account, and we ask for consent before we go off and fetch any open banking data. It's really important to highlight we're regulated by the FCA, and we have to make sure that everything is done with consent. And we've actually spent a lot of time improving our Connect flow and our journey and increasing conversion. Conversion is better for everyone. Lenders want to see people going through the journey and actually going through the application process and linking their bank account to actually get the credit check done. We obviously want to do a credit check as well on people and collect the data and process it. Once we've got that data, we want to categorize it. So when we talk about categorization, we're looking at a list of transactions that come through on your bank account and grouping them essentially into particular areas. So you can see here as an example, we've got someone's rent coming out under housing, council tax, loan repayments, etc. And we use a couple ways of doing that. We've got a rules-based approach where we might say, look at a list of councils around the UK, and we might match against that at a very simple level. But then we also use machine learning as well to do something more predictive and work out what a particular merchant should be categorized as. And we match everything against a set of standard categories used within the financial sector as well. So it matches up quite nicely to what our clients would expect. And then the final part is that we enrich the data, which means we go through and we work out scores and generate insights there. And we're constantly working with our clients to enable new features and working with the market conditions as well as we go through things. Our scoring model is very predictive, and we can offer kind of bespoke things as well for different clients as well, whatever they need in their particular use cases. The other two product areas worth mentioning are Atlas, which is our dashboard tool used by our clients, and then our reports API as well, which is a REST-based API behind the scenes that clients will integrate with. So I'm going to jump now into kind of more of the technical part of our talk. So beyond the 2.1 billion, I'm sure some of you have probably guessed what the 2.1 billion refers to, but I'll dive into it now. So a bit of history. Our platform was initially built on Ruby on Rails. This was probably about 3 or 4 years ago now, 2018-ish. We use Postgres as our main database, and Ruby on Rails, sort of, when we create migrations, defaults to integer columns for primary keys, or it did at least back then. And integer columns have a limit to the number of integers they can store, which obviously becomes a bit of an issue over time. So I mentioned the Postgres database there. This is a very, very gross and crude mock-up of kind of the architecture and where our database sits. But the idea is that it sits at the core of everything. So one database instance feeds all of our products used by both sides of our user base. And the data inside, obviously Postgres is kind of going to be tabular. It's a relational database. We've got columns here and relations between things. And this example here kind of shows the type of data we might be storing in our database. There's a lot more to it than that. There's over 300 tables. But the transactions table is an important one, I think, to highlight, because when someone links their bank account to Credit Kudos, we go off and fetch their data from open banking. And our volumes have increased over time. So we're often fetching a lot more reports and a lot more data every day. But also we're able to go back through the history and fetch hundreds, if not thousands, of transactions. And with open banking, we also get access for up to 90 days after linking the bank account. So we can also go back and generate a new credit report later on down the line when the lender is ready to process the application. So the limitations for integers are 2.1 billion for integers themselves. The next step up is huge. Big integers are 9 quintillion, 223 quadrillion, 372 trillion, 36 billion, 854 million, 775,817, which is obviously a lot more numbers, and that's where we'd like to obviously get to. I'm sure any business would love to have that much data in their database. So we've run out of numbers, but we're actually in good company. YouTube had the same issue back in 2012. Gangnam Style reached the limit on the number of views that they could store, and they had to do a big upgrade on their database to continue counting past the final number. So they've been through the same journey that we've been through recently. And one of the key things for us was we knew that we had an integer column from the get-go across all of our tables. We like to monitor and ensure that we have instrumentation on things and observability into our systems. We use Datadog quite a lot for our infrastructure, but also increasingly more for our application logging and performance management, things like that. And we were able to build alerts and logging around how many integers were left in our columns, and work out which ones were the ones we needed to upgrade. So as an example, you can see here that the open banking transactions table is the one that was obviously growing quite quickly at the time, followed by a succession of other tables that were linked to the open banking transaction as well. And the other thing we use with Datadog is our disk space. So obviously holding all this data and having numbers is one issue, but obviously each row has got multiple columns in it, and each one of those takes up bytes on the disk, and that obviously piles up. So our disk is actually 5 terabytes in size, which is a fairly large size for a database. But what we've discovered is disk space in Amazon is very expensive, and we need to be able to manage it very carefully, and keep an eye on how much we're using, and obviously bump things up when we need to. Datadog's got some cool features that we managed to make use of. So we were able to forecast when we were going to run out of space and be quite reactive to things, and be able to plan well in advance any work that we needed to do on our database. And it's important to note that we did all of this whilst keeping service with our clients. There was no impact on them at all. They didn't know that a lot of the work we were about to do was coming. So the aim was to basically move our primary key from being an integer to a big integer, which sounds simple. The steps we took were to create a new table using a big integer column, copy all the old data from the old integer tables across, and then migrate the whole platform to use these new big integer tables, and then to balance the disk space and our Amazon bill, delete the old table. Why do we go down this route? Well, because there's 2.1 billion rows potentially in that table. And if we ran an alter statement on that, it would lock the entire table. And Postgres probably would have got there in the end, but it would have meant that no one would have been able to use our application for the next foreseeable days, probably weeks, whilst it ran through and updated all of those columns. So quite a painful operation otherwise. So there's a few challenges with the approach that we had. First of all, how do we copy the 2.1 billion rows of data from one to another? We had a couple of discussions on that, some ideas around, do we use triggers and do something like an insert on one would insert to another? How do we also make sure that we're monitoring that and know that data is copied, and how long will it actually take us as well? And how do we keep things up to date? So if these jobs take a while to run, how do we make sure that since the last time we ran it, any new data is put into the new table? And then also we've got to hold both the old and the new whilst we're copying. So potentially 4.2 billion rows there that would be for each table. So it'd be doubling our disk usage in the short term. And at what point do we switch everything over to using these new tables, and how do we coordinate that? We don't want to be in a position where we're reading from the old tables, writing to the new, or reading from the new and writing to the old. We want to make sure that the entire platform is reading from one canonical data source at the same time. So a couple of ways we solved it. We used jobs. We used Sidekick, which is a Ruby worker and queuing system based on Redis. We used that to parallelize the jobs and to scale up using workers. In the end, it took us approximately 7 days to complete the copying, which is pretty impressive, I think. And then we focused on getting the most recent data copied first and have scripts to backfill any of the missing data, any of the older data. The nature of our business is that we generate a credit report, but it's only really valid for the point that a lender is looking at somebody. So we don't necessarily need to have to hand a credit report generated 4 or 5 years ago. We're more interested in the immediate or the present and how we can store the data for lenders to make a decision today and this week rather than years ago. We also need to carefully monitor the disk usage. So we did increase our disk space. We bumped it by another 500 gig. It's added to our bill, but actually we're able to obviously decrease the size of the disk once this piece of work is done. But it's a lot easier to increase than it is to decrease. Amazon can upgrade a lot of things with a click of a button, but going backwards is a lot more difficult. And then finally, we switched things over using a feature flag. So we deployed all of our code bases with a feature flag and was able to flick things over with a flick of a switch. And suddenly we started reading from the new tables. So that piece of work is all now done, and I'm happy to say that that's no longer an issue for us. Our Postgres database is running on big ints, and all our services are running on the new tables, and there was no disruption at all to our clients or to service, which is a huge achievement. Beyond that, where do we go next? So a little comment here from Dilbert, but thankfully I'm not Dilbert's boss. I'd rather we looked at lots of different solutions going forward for different jobs, rather than just adding another SQL database into the mix. So some of the things we've kind of learned and some of the things that we're very conscious of going forward is that a relational database is expensive. We pay per gigabyte of disk space that Amazon provisions for us. We pay for the amount of CPU and memory, which all costs by the hour. So it equates to roughly 1/3 of our Amazon bill at the moment. It's also very time consuming to manage. We've got a dedicated platform team, but would rather be working on more exciting projects and improvement and performance gains rather than trying to sort of shift things around and solve impending risks and things. And also very difficult to scale. So we can scale vertically quite easily, but horizontally is actually a little bit trickier. How do we replicate these servers? And obviously that will duplicate the bill for each instance that we're running as well at the same time. So some of the things we're doing going forward is we've looked at our data and we thought about how do we actually want to store it. And one way that we're keen to progress is to use protocol buffers, which we've been using now for nearly 10 months. Protocol buffers, or protos as we call them for short, created by Google. They're language neutral, so you can load them into any programming language, and you get the types to come with it. They hold serialized data. They're kind of like XML, but smaller and faster. I kind of think of them a little bit more like JSON schema, if you've ever worked with that. And they've kind of inherently also got a bit of validation in there as well, because they're typed, as you can see on the right-hand side, there's an example. And one of the interesting things for us is they can be stored as binary files, which means we can leverage file storage in the cloud rather than databases. So yeah, the way we're trying to store data going forward is to have a report which can be stored in a single proto file. We found that our reports are roughly about 200 kilobytes in size. It varies depending on the use case and how much data and how many accounts are linked to each report. But we can store them quite cheaply in S3. So S3 is usually in the region of pennies per gigabyte. And then we can also look at using protofiles to be passed into services. So we get this atomic unit that we can move between different services and pass around, which is useful for us. And then from a compliance perspective, we can also manage permissions and things through S3, through Amazon. So in a traditional database, we might have a username and password and a set of credentials that we'll dish out to a set of applications. And then we have to go in and create grants and other kind of permissions and roles for each type of database use case for that application. With Amazon, we can actually leverage IAM permissions. So we can give individual users in our company access to certain files, paths and directories in S3. We can also log through CloudTrail access to files through S3, which creates a nice audit trail. And there are various other things that we can look at as well. So we can look at encryption and versioning as well, and replication across regions much easier. So the natural progression for us post Protos is to go down the gRPC route. gRPC is actually a recursive acronym. gRPC wrote procedure call, in the same way that GNU Linux is. GNU is not Unix. gRPC is a low latency, highly scalable remote procedure call system. It makes use of protos, and it's also HTTP2 and bidirectional, so quite fast. And for us, it's a natural progression as well from using REST APIs internally to talk to each other. We can call particular methods on different endpoints in our system. We've been using gRPC now for probably 10 months as well. We've delved into things like service discovery, app mesh, and other tools that Amazon has given us. And there's some really interesting features in there, like TLS between services and other things that we're starting to work with as well. And with all the data now suddenly no longer available in a relational database, we need to think about how we want to access it and query it, and actually have something tangible that we can use for reporting and sort of understand what's going on with reports. So Athena is an area that we've invested in more recently. Athena is a serverless database, uses SQL. It's quite fast at returning results, not as fast as BigQuery, which we've experimented with, but it suffices for what we're using it for. It's quite cheap to run, so you're paying by the terabytes of data that you're querying in your data source like S3. And again, we can manage everything quite nicely with IAM permissions, so it ties together nice and easy for us. And we're starting to work on some data engineering projects coming up on how we can get our protos into a format that Athena can use and we can query from. And Apache Parquet is one of the routes that I think we'll be going down in the future. So if any of that sounds interesting and you want to kind of come along and work with us, our tech stack overall is Go, Rails, Python, TypeScript, AWS, Terraform, Docker, gRPC, React, to name just a few. Give us a shout. We were hiring for senior engineers and platform engineers at the moment as well. Thanks.
Thanks a lot, Adam. One quick question. How long did it take you to learn how to pronounce this big number?
It's become a bit of a meme in our company. I did a presentation internally and I read it out, and yeah, we've now it's become a bit of an ongoing thing in the company. I think we were joking about having drinking games and things like that with it, but yeah.
Yeah, no, I really enjoyed your talk, and I think, it was fascinating to listen that, while still being, fairly young and early stage company, you're already managing such a huge amount of data. Like, how do you how do you look, like, do you envision like the challenges that are ahead of you? Like, once you're gonna become, let's call it, mainstream solution, like, what do you think are going to be the challenges, and sort of like how you're preparing your product for it right now?
Sure. So yeah, scale is our main thing at the moment. We've got a lot of clients, and it's just about signing more of them and improving our volumes and things going through the system. So at the moment, we use a lot of workers and Sidekick and Redis and things. I think at some point we will have to move to sort of more message queues and pub sub type technology. So I think that's one area that will benefit soon. And then our data engineering piece is quite a big piece for us going forward. As we're growing as a company, we're going to be probably bolting on things like business intelligence and other roles and research into other areas. We're collecting outcome data from loan companies that we need to ingest as well. So taking on all this data and being able to get it into the right places so that we can actually query it, manage it, drive out insights from it is really important. So I think much like the other talks today, things like PubSub, Airflow and DAGs will probably feature at some point in our architecture, and Kinesis and Kafka will probably be a decision we'll have to make as well at some point.